But first, please subscribe to the channel, click on the like button, click the bell icon to get notified, and support me on Patreon if you can. There's a link in the description below. Hi, welcome to number 5 in our expert series. This presentation is dedicated to all programmers who have asked themselves why their app keeps crashing randomly on ESP32 or 8266. And in my experience, I expect that to be quite a large audience. What I'm going to look at is why it happens. Now then, I said that all of the libraries I know are broken. Let's say I only know 4, but they all are. The first one is so awful that I've already made 2 videos just on that one library, so we're not even going to touch on that today. ESPAsyncWebServer has a few problems of its own, and I'm going to make a separate video on that. But I'm going to concentrate today on ESPAsyncTCP, which runs on the 8266, and AsyncTCP, which runs on the 32. Now, before we go on, you have to realize that the 2 top libraries that we're not going to cover today both call either one of those 2 lower libraries, depending on what target you compile for. So to a certain extent, the problems in those upper libraries are inherited from the problems that we're going to look at today in those lower 2 libraries. But ESPAsyncWebServer has a few problems of its own on top of those, and I'll cover those later. However, let's move on. A very brief summary of what we mean by async. The arrow of time moves forward. In the top diagram, we have a request that we make to some external resource at T0, and an async or non-blocking library returns immediately, allowing our code to do other stuff, and then at T1, when that resource is available, we get called back to say, hey, I've got it for you. That's called non-blocking because your code never stops running. Blocking libraries, when you request that resource, it goes off and it waits until it's ready, and then it comes back. So your code doesn't even run in between those 2 things. It is blocked from running, hence the name. Now, why am I talking about this in a presentation about async libraries? That will become apparent shortly, because the problem with at least one of the libraries we're going to discuss is that it calls itself async, but it can't actually operate correctly in async mode. So that first one we call overlapped. Well, I call it overlapped because the other stuff that you can do in there is make a second call to another resource. So that call starts before the first one's even finished, hence they're overlapped. With the lower thing, all you can do is what I call ping pong. You call the external resource, you wait, it comes back. You call the next one, you wait, it comes back. Back, forward, call, wait, ping pong. Now then, is it possible for a library to be called async if it only operates in that bottom mode? It doesn't block. You can still do stuff in that code in the middle. So it's not strictly blocking, but it only works if you alternate the calls. If you overlap them, it fails. Now then, before we get into the real nitty-gritty of the statistics and proof and evidence, there's 2 phrases you need to understand. There is a value in the LWIP library, which all of these things call, which actually manages the network, called TCP send buff. And that is the number of bytes that are available for sending and receiving TCP messages. It depends on the architecture and or the choices you make in the build tools. Those are the values there for ESP8266 when you choose low memory and when you choose higher bandwidth, and what is currently on my Dev32 board for ESP. Others may have different values. I don't know, to be honest, but that's the point. The point is this, is that neither of those two libraries can send a packet that is bigger than those values. So if you are to avoid all of the pitfalls I am about to describe, you need to know what those values are. And that's not just one packet. You could be sending 2 of 536. That adds up to 1072. You're fine. You send 3 of those in a row, it'll fail. So you have to know that send buff to stay within the boundaries of what these libraries can do. The second thing you need to understand, you don't need to understand, but you need to be aware of, is a thing called the Nagle algorithm. It's named after a guy called Ralph Nagle, I think. And it's a way of minimizing the overhead involved with sending lots and lots of small packages. So what the Nagle algorithm does is it doesn't send immediately. It starts filling up a buffer, and then when the buffer's full, it sends the buffer. Or if it waits a certain time and hasn't had any more small packets to put in the buffer, it thinks, well, I'm not going to hang around forever. I'm going to send it now. The point is this: you cannot predict when that send occurs, nor can you predict how rapidly that buffer fills up. And for that reason, it massively complicates making any of these libraries completely predictable. So it's all about buffers, and it's all about the internal system juggling with them behind your back in a way that you can't control. Well, you can turn the Nagle algorithm on or off, but you need to understand what it is and why. Right then, so what's wrong with those two libraries? The best way to describe it is to show you a library that doesn't exhibit any of the problems, which is the new H4 AsyncTCP library that I've written specifically so that I don't have to use these other two libraries with all the problems I'm just about to describe. So, the top two libraries cannot handle a large packet, and by large packet I mean anything that's over the size of that TCP send buff, or a combination of them over a period of time that add up to more than that send buff. It's very complicated. They can't successfully handle consecutive transactions, which means that if you say send, i.e. you're trying to use that asynchronicity, if that is a word, and if it isn't, it should be, it doesn't work. It just fails. It just throws the second one away, depending on the size of it. And that is kind of tied together with not handling that overlap correctly, i.e. not actually operating in an asynchronous fashion. Now, the reason why AsyncTCP has kind of got a yes, no, sometimes, let me say at this point, AsyncTCP isn't a particularly bad library, I don't think. It can do consecutive transfers. It doesn't fail or crash if you try, but if you exceed that complicated algorithm that we haven't got time to explain, there are circumstances in which it will throw data away. Having said that, they are very rare, and you have to be what I call pushing the envelope, sending lots of very big packages very quickly. In that circumstance, it will fail, but it does it in a kind of half decent. I mean, it doesn't crash and give an exception. It just throws the data away. I mean, which is worse, I don't know. However, it's the same with handling overlap. Having said that, if you stay within its boundaries, which, given the much bigger memory buffer size and the more powerful ESP32, pretty much suit everyone, which is why half the people watching this will say, what's he talking about? I've never had a problem with AsyncTCP, and quite frankly, neither have I. However, read on. The same cannot be said for ESPAsyncTCP, which doesn't do any of those things. And if you try and step outside of its very, very small, narrow envelope of where it works, it will crash and fail, and it will just... Let's look at the facts. Those problems will result in data loss. And the worst part of that is you never get told. It just throws the data away. You don't know it's gone. You think you've written it, you haven't. Those errors generally, especially on the 8266, result in an exception and a crash. There is a third problem that both of those libraries exhibit, but it's very, very subtle and it's beyond the scope of this presentation, but they are both liable to data corruption and or crashing unless you use them very carefully, and the documentation doesn't make that very clear. Having said that, you kind of have to try hard to do it, but it's there. Okay, and obviously the whole point about this whole process is that I've written AsyncTCP specifically to avoid all of those three problems, so it doesn't exhibit any of those behaviors. It'll have its own bugs in it. I'm only human, or almost human, as some people might say, but at the moment it doesn't do any of those things. What makes this difficult, and the reason why some of these bugs have taken me literally months and months and months to tie down, because they depend on things like network latency, the receive rate, the packet size, the loading of the MCU, how busy it is. You know, has it got time to do other tasks? If it's doing other tasks, it can't be unloading the queue, so the queue grows, and that depends on the rate at which you send them, and then that depends on your network latency and your network speed. It also depends on the size of the send buffer and how fast you're sending, and the speed of the MCU, and whether you're using the Nagle algorithm or not. And together it makes an unholy soup that is absolutely impossible to predict with any degree of accuracy. About the only thing that doesn't affect it is the price of fish. So what we're going to do now, just to show you the problems, because it's all right, all well and good listening to some bloke on the internet, but if you're anything like me, you want cold hard facts and statistics, and that's what you're going to get now. So I have built a very small echo server with Python, and all it does is listen on port 8080, and it just sends back any data that you send to it. So I've then got a test program which sends n packets of size S at an interval of t, and all of those things are things that you can compile in and out and change easily so that you can set up specific tests. And some of those will be done with the Nagle algorithm, without the Nagle algorithm, so that you can see the difference. And that's pretty much all it does. So the tests themselves that we're going to run 4 tests on each of these libraries on the different hardware. Test 1 has to succeed. It sends 1 packet the size of the maximum allowable thing. So if a library can't pass that test, it's not a library. It's a piece of random code that doesn't work. So every library is going to pass that test. So the time between packets is irrelevant because we're only sending 1. So if it can successfully send 1, which they all can, we then say, well, can it then send 2 in a row? If it can send 1 at max value, why can't it send 2 at max value? Now, when we try that with 0 time in between them, so we say send, send, sometimes it works, sometimes it doesn't. But I'm jumping ahead to the fun part. Test 3 is to then send a packet which is deliberately bigger than the maximum buffer size allowed. I just multiplied it by 1.5 for a bit of fun. And again, we send, well, that's an NA as well. But you can adjust those parameters and send 3 or 4 of those in a row and see what happens. And then finally, so all of those tests, sorry, jumping ahead, all of those tests are to do with the buffer size and the buffer handling. The 4th test is to do with the speed, and whether it's fully and truly asynchronous. Because what we do there is we send 20 small packets in a row. Now the size is chosen to be a 20th of the send buff, which means that they have to fit in. They will fit into that send buff. So there is no, we've eliminated anything to do with the buffer about why they won't be sent. So the only thing that's left is that if they don't get sent, it's because of a timing problem and or an overlap problem. And what we can do then is we can start playing around with the interval between them and see if there's a point at which we can slow it down to the point where it actually works if it doesn't do to start with. And again, I've rather preempted what's coming next. So those are the 4 tests we're going to run. Here now are the results. There'll be a table at the end. You don't have to look at all the data in this, but basically just to show you that what we're asking is not impossible, it's not unfeasible, and it's something that can perfectly easily be done without any problems whatsoever on both ESP32 and ESP8266. Here we have H4 AsyncTCP running test 1, test 2. As you can see, we're not using the Nagle algorithm. It just makes life a lot simpler to start with. Send buff on this installation is 5744. There we go, 1, 2, 3, 4, and on average we're sending 215 bytes per second. When you scale it up, obviously we're only sending a very few small times, but that figure's interesting for the next couple of slides. So there we are. Boys, it can be done. So there's AsyncTCP running exactly the same code. I've just got a little if-def at the top of it that compiles for one or the other. It fails on those middle two, so it can't send that big packet. And if you look what it can send, it sends the maximum size packet. That's all it can do. If you send 2 of them in a row, it fails. It only sends the first one. Test 3, a deliberately bigger packet, fails again. All it does is send the first lot of 5744. It's totally and utterly throttled and strangled by the physical size of that buffer, which, unless you dig very, very deeply with a big spade, is quite tricky to find. So from a user point of view, not very helpful or friendly. On the good front, and the reason why this library isn't as bad as the other one, is that it will quite happily send those 20 small packets because it doesn't have that overlap problem. But look at the effective BPS, 161. Now, okay, it's not exactly representative because those middle two failed, but on the figures that we have got, H4 AsyncTCP is actually faster, as well as being more stable and more functional. Right, let's switch to the 8266 now. WeMOS D1 Mini. Nagling is false. Again, that complicates everything. Quick slide just to prove that it can be done and get us a rough figure for that BPS. Now then, here's an interesting point. Look at this figure here. All of these get dispatched in 20 odd milliseconds. Sending the 20 packets takes 10 times as long. And the reason is because we're not using the Nagle. So for every single one of those packets, it has to do a send, and that's got an overhead and blah, blah, blah. So your average drops down greatly, and that brings the whole average down to about 116. So let's see how ESP AsyncTCP manages with that. So, bit of a problem in that only the first one works. That's the only thing it can successfully do, is to send one packet of its maximum size. All the others fail for various reasons. And look here, here's what's really interesting. If you look at the figures in the previous ones, the failures in ESP32, it sends the maximum amount it can, and that's it. The amount that it sends in this case on the ESP8266 is some kind of weird random figure, and that's going to come up later, so watch it. And It's really, you can't compare the two, can you? It's not effective. But what that shows us is if we use the Nagle algorithm, we should get a much better time on the lots of smaller messages, and that's exactly what it's designed for. So let's run that up the flagpole and see who salutes it. So here's AsyncTCP. As you can see there, nagling is true, and as you can also see now, look at that time there. It's now down to about the same as all the others, because basically Nagle just waits and fills up the buffer and sends one buffer. That's why the time is almost the same. And of course that then raises our effective throughput to about 157 bytes per sec. Let's see what ESPAsyncTCP's response is to that. Oh dear. Not only can it not do it, but it throws an exception and it crashes. Now, to save a lot of time here, because I've spent a lot of time testing these things, to save a lot of time, I'll tell you this now, is that any time you use the Nagle algorithm, any of these tests with ESPAsyncTCP, it crashes. So for all the rest of the tests on 8266, the nagling is going to be false. Because if it's true, it will crash. And that is a fact, and that's the end of that. So we can't measure that. So what we're going to do now, since we can't measure any of those other things on ESP8266, what we're going to do is we're going to look at just running that last test, and we're going to start changing the amount of time that we delay between each of the sends, because I've told you that it can't do that overlap. So what we've got to try and do is stretch the time out between sends so that we avoid the overlap and we get into the safe but completely non-asynchronous ping pong ping pong. I started at a very high value, like about 100 milliseconds, and I worked back down and I worked back down, and I'll tell you the results in a minute, but this is just an example. Here we've got 15 milliseconds between each of the 10 sends, as you can see. And there we are, look, the first one works fine. What's all the fuss about, Phil? Well, because if you see, less than a minute later, I manually reboot it, and the very next thing it does is crash. Exact same code, nothing's changed, nothing different whatsoever. And if that ain't random, I don't know what is. So let's see if reducing it makes it any different or better. Let's take it right down to 1 millisecond. Now that's near as damn it like the original test, which had 0 seconds between each other. But there we are, look, 1 millisecond between each. It just does not work, will not work. Two milliseconds between each. Doesn't work. Reboot, it works. Reboot again, it doesn't work. Reboot again, it doesn't work. There is nothing different whatsoever between any of those instances of that code. You can just look at the times. That reboot was at 39 minutes and 34 seconds. The next one was 39, 10 seconds later. Right? 10 seconds later it fails. 57, reboot again, 43 minutes later. Is that 3 minutes? No, sorry, 39, 50, whatever. You take my point. It's just utterly impossible to predict whether it's going to work or not. And that's about as random, kind of the definition of random, isn't it? Let's see what happens at 3 seconds. 3 milliseconds between each. Oh, look, it's starting to get okay. Except we know it isn't, because we've seen even at 15 it still breaks. But look, 3 in a row, perfectly okay versions. Again, they're like, I'm basically sitting there hitting the reset switch each time it does the results. 3 in a row work, next one fails. I mean, it's just insane. It's unusable, it's unworkable. 4 milliseconds. This is where it gets really fun, folks. Look at that. I said we'd turn off the nagling. We have. It's false. There's your proof. So at 4 milliseconds, even with nagling false, it'll crash sometimes. Because look at this. At 13:30:35, it crashed. I've cut out a lot of that junk. So it restarts itself less than a second later. Within 2 or 3 seconds of making a connection, it's worked. Exact same code, no different, nothing has changed. And that's with nagling false. So ESP AsyncTCP is chaotic. And I'm not using that word just like as kind of random slur. I'm using it in the mathematical definition of the word, which is that even though it's code and then therefore should be deterministic, it's unpredictable. And the key thing about chaotic theories or systems in mathematics is that the tiniest difference in starting conditions can result in a massively different ending conditions. And my favourite example is the Rocky Mountains in America. It's raining on the top of the mountains. At the very peak of the mountain, a raindrop that falls at point X will flow into the Pacific Ocean, and a raindrop that falls 1/10 of a millimetre away from it ends up in the Atlantic Ocean. So that tiny initial starting point, the end point, is and that is what ESPAsync is like. You make the smallest change to any, remember those? Make the smallest change to any one of those, and it will crash or work or not work and not crash. It is totally and utterly impossible to predict. And that, my friends, is why your ESP sketches crash. Because if they use ESPAsyncTCP, all of that nonsense is going under the hood for free. Let's have a look at the summary then of what we've seen so far. In terms of the table of tests, that's the raw data. So H4 deliberately designed to have green crosses in all those positions, green ticks. ESP32, yeah, we've talked about that. If you're very, very unlucky, you can get that, but I'm gonna give that 2 greens. So the only thing the 32 can't do really is send big packets or lots of big packets in quick succession. By contrast, the only thing the ESPAsyncTCP can do, the only thing it can do is send small packets at a very slow rate of speed. And if you step outside of those parameters, you will crash or fail or throw away data or corrupt data, depending on, toss a coin. Summary then by library. Library passes H4 AsyncTCP passes all the tests. It doesn't matter what size packet you send or how fast you send them. That is the mark of an async library. And it's limited only by the amount of free heap you've got. If the packet that you're trying to send can fit into half of the memory, because you're probably going to want to receive it as well, so there's going to be 2 copies, then it will get sent and it will get received, and that's the end of the story. And that's all you need to know. In fact, that's all the library should do. AsyncTCP is stable. It doesn't crash very often at all, but it can't send large packets or successive packets that collectively, according to that horrible soup of variables, exceed the send buffer at any given point in time. So it's a little bit unpredictable, but you've got to be unlucky to get there. ESPAsyncTCP, well, what can I say? You've seen the facts, you've seen the evidence, your own sketches are probably what brought you here in the first place. It's unstable, it's chaotic, it can only do one thing, and even then it doesn't do that very well because all the other code's faster. However, what makes it really fundamentally nasty is that other libraries depend upon it for their asyncness, and therefore they inherit all of its flaws and problems. So at last now we've got an answer to the question that the thinker had on the initial slide, haven't we? We have reached enlightenment. We now know why our apps crash randomly on ESP32 and ESP8266. And there's the reason. Those 2 libraries. just a footnote. Hopefully by this point you'd think, well, why would anybody else want to use anything other than H4 AsyncTCP? And here's the reason: because it's not ready yet and it's not finished yet. There's a lot more testing to be done on it. All I've done is get the core part of it working to the point where I can make this valid comparison. So what I've got to do now is put in all of the kind of weird edge case error paths, all the low heap prevention, and then I've got to do a full integrated systems test with AsyncWebServer, and that's H4 AsyncWebServer. And again, that's the point when I'll make that video, because H4 AsyncWebServer is written to avoid the additional problems and bugs in ESPAsyncWebServer. Then I've got to integrate it with all of the other portions of code that make up the whole H4 plugins family. So Async MQTT, that's got some special requirements of its own that takes a lot of testing. And then I've got to integrate the full test of all of those parts with the new version of H4 plugins, which will probably be version 4. So there's a lot of work to do. But mostly it's testing, and so I'll be grateful for any help. Anybody that feels that they're in a position to be able to test these things, get in touch with me via the groups or through the YouTube channel, or do whatever. And until then, I hope you found this interesting and informative. I hope it's given you hope for the future for stable ESP apps. That's the only reason I've spent the last 3 months doing it, for my own apps. And as soon as I get those stable, obviously I'll share them with the world. And that's about it. Thanks for your time. Look forward to making another one for you soon. As always, thanks for watching. Please remember to subscribe, like, click the notification button, and support me on Patreon if you can. Thanks, and see you next time.